Hi, my name is Kashab, and today I'm going to present on my project, which is predicting the movement of satellites using machine learning. I was interested in learning more about satellite orbit predictions and decided to do it as part of my machine learning project. So for my project, I use a Kaggle dataset with 3 files from the IDAO 2020 competition. This dataset contains data from 600 satellites that are in LEO, MEO, and GEO orbit, or geo orbits. And the 3 files are gen-test, gen-train, and answer-key that are in the dataset. The overall goal of the dataset is to predict the true kinematic states of 600 satellites in orbit around the Earth for the final 7 days using the shortest computer runtime. So to understand kind of how satellite orbit prediction works, this picture I feel like demonstrates kind of a good example. You have the estimated and true states of the satellite, but at the very end, you have 3 states, and those 3 states are what the 3 files represent. The predicted state, the machine learning modified state, and the true state um, each represent a state that is given by the file, and then based upon where that state is, we can make comparisons and see how far off our predictions are. So let's get more into the data. The first thing is for the gen-train file. It contains both the true and the simulated kinematic states of the 600 satellites for a 24-day period of time. This means that all the data variables are contained there, whereas for the gen-test, it only contains the simulated kinematic states, so there's no true velocities or positions. And finally, answer-key contains only true kinematic states of the 600 satellites for the last 6 days of the month, meaning that it only contains true data and no simulated velocities or positions. Um, to kind of illustrate the differences between the data, I kind of included this diagram, and it presents kind of which is used for training, testing, or both, the total number of lines, what's simulated, true, or both, and finally the time period of the samples. For the first, what gen-train and gen-test, you can see that they're both used for training, whereas gen-test and answer-key are used for testing. Then afterwards, gen-train is different than the gen-test and answer-key files in that it has more lines of code over. And when we compare, it's 50,000 lines of code versus 14,000 for the other 2 files. It contains both the simulated and a true, whereas the gen-test contains simulated, answer-key contains only true states, and finally, it has first 24 days of data of January 2014 provided, whereas the gen-test and answer-key contain the last 6 days of January 2014. Now to go into the details about the variables. The first variable is ID, and it represents the unique row identifier. Next, you have the epoch, which is like a date and time that's provided to give a time of when the sample was taken. Then you have sat-ID, which identifies which satellite is being tracked. X, Y, and Z represent the true position coordinates of the satellite. Vx, Vy, Vz represent the true speeds of the satellite. X-sim, Y-sim, and Z-sim represent the simulated position coordinates of the satellite. And finally, Vx-sim, Vy-sim, and Vz-sim represent the simulated speeds of the satellite. So as you can see, the gen-train has all the data variables present. And then afterwards, the gen-test only contains the simulated positions. So that's why only the simulated x-sim, y-sim, and z-sim, along with vx-sim, vy-sim, and vz-sim are present. Whereas the answer key has the true kinematic states, so that's why x, y, z, and vx, vy, and vz are present there. Now let's get into the methodology. So I used for the base code sample a code provided through Kaggle. I made some changes to this code and basically then afterwards ran it. And so as part of this code, I first used the min-max scaler to scale kind of the training data or the X data. After that, I changed the epochs to date and time to identify the time frame properly within the program. I created two arrays, one that had the true states and one that had the simulated states. Then I split the training data set into 90% training data, 5% holdup validation data, and 5% test data for testing the model or training the model. After that, I fitted the training data for getting a training accuracy score. Then I printed out the training score, accuracy score. Then after that, I imported in the test file into an array, and then used a min-max scaler to scale the testing data for use in regression modeling. And then after that, I printed out the testing accuracy score. So this is kind of two samples of the code. As you can see, the x, y variables are created here, and you have the simulated data in the x array, and the y array has the true states. Also, you have the date. You can see the epoch being converted as well in that. Then afterwards, the x data is being scaled. So you can see that it's being, you use the min-max scaler from the pre-processing module from Python, and then that is transformed. Later on in the code, we're going to be using random forest regression in this coded sample, and so 100 trees was used for this. So it's imported in this regression algorithm. And then afterwards, the training data is fit using the regressor, and then an accuracy score for the test data is printed out. Afterwards, the test data is imported into an array and then scaled once more again and transformed. After that, it's the accuracy score for the testing data versus the answer key data is given. So after I ran that code, I decided to make some changes and try to improve the algorithms. So first, I tried to test out multiple regression models to determine which one was the best. Then afterwards, I removed satellites to determine which ones I needed to see if I can improve the predictions and see which two were the best. And then after that, I changed the scaler and the amount of testing and validation to see if there were any improvements for the two that I thought were the best. Afterwards, I also used metrics to find information about those two, and then finally tried to improve the hyperparameters for those two algorithms that I thought worked best. My results from it included that determining that the KNN and the XGBooster regression algorithms are the best regression models, as they had the highest accuracy scores and the lowest computer runtimes. Removing the satellites from the data increased the predictions slightly, which led to better predictions in both the training and testing. Changing the scaler for the KNN also improved it, as I ended up using a standard scaler, whereas the XGBooster didn't really have that much change. Similarly, or in a different kind of way, changing the amount of validation and testing data for both didn't really have much of an effect at the end of the day. Then afterwards, I determined metric values that include MAE, the MSE, and RMSE. All of the values for the KNN algorithm were much smaller in comparison to XGBooster. And then more importantly, the RMSE and MSE were higher than MAE, and that showed to me that there were a lot more errors in data than I thought originally. Finally, I tried to increase the number of neighbors in the KNN algorithm to see if I could increase the accuracy, but it failed. So from the first experiment, you can see here, this is just for the 600 satellites, and you can see the training data in the first column, the test data in the second column, and then finally the computer runtime. So as you can see, KNN and XGBooster are the highest in terms of not just the in terms of the test data accuracy and the computer runtime. And even though the decision tree and random forest had really high training times, their test data accuracy was really low. Similarly, you could see here the same thing, but this test is used mainly for the 400 satellites that were removed. And you can see here that the training data was high, as usual, for the same 4 algorithms. However, the XGBooster and KNN had the highest testing data accuracy, and the computer runtime was, even though it was high in the XGBooster, it was still a very good score for it. Finally, here I wanted to kind of present the results and show kind of an example of how the MAE, RMSE, and the training score and testing scores kind of showed up. As you can see, as the number of KNN trees kind of grew, it kind of decreased the testing score. And the number of samples for the KNN algorithm increased, it kind of decreased the testing score. So that's why we only used one. In the end, some areas of improvement that I really wanted to improve included plotting and visualizing the data, as I need to understand or figure out where the errors were occurring with the predictions. I also felt like I could have improved upon the algorithms by removing repetitive data, as I thought it will reduce the time for the algorithm to run and help to improve the predictions. And finally, using K-Fold's cross-validation or grid source CV so that I can kind of understand the flaws of data and, more importantly, improve the algorithms at the end of the day. And then finally, for future work, I wanted to try and see if I could obtain more features to improve the accuracy of the predictions made. I also wanted to try and test with other satellite data to see if I can maybe keep the same algorithms and test it with other satellites and make it more universal. And finally, use more data about space debris as well as incorporate drag force for LEO satellites so that I can improve the orbit predictions at the end. And with that, that's it. Thank you so much.